Hi everyone, so this is going to be our first video talking about latent heat. This is the first attempt at having a digital classroom, so you'll have to bear with me on this one. But basically we're going to flash back to last week where we did an experiment. We had the two test tubes of liquid, one had water, one had something called cetyl alcohol in it, and we cooled those liquids and we took recordings of the temperatures as it went down. And we noticed that as the chemical cetyl alcohol was cooled and transformed from a liquid to a solid, the temperature stayed at around 46 degrees for that entire time. Okay, now that's really important, and it leads us to what we're talking about in terms of latent heat. Okay, so latent heat is the concept that inside every chemical on the planet, there's a latent amount of energy that can be applied to it to turn it from a solid to a liquid to a gas, or that same amount of heat removed from it to turn it from a gas to a liquid and a liquid to a solid. So what we have in there is this heat energy that is required to break the bonds of those molecules apart. Okay, so in order for us to change from this solid into a liquid, okay, what we have to do is increase the amount of energy. Okay, so energy is added to break the bonds. Right, so if we're moving up this scale from solid to liquid, liquid to gas, energy is added to break those bonds and pull those molecules further apart. Okay, and if we're moving the reverse, we're going the opposite direction and moving from gas to liquid or liquid to solid, energy is removed. Okay. To allow the bonds to rejoin. Okay, now what we do in this section is we look at the different changing states and the amount of energy that's required for that. Okay, what I will add roughly here is there's going to be a big data sheet, okay, which gives you the values for the specific heat capacity and the specific latent heat, okay, because all of those will be important. Now, to change state from a solid to a gas, you have to add in quite a lot of energy, okay, and so what we're going to be looking at is that, and it's also dependent on the mass of the chemical you're dealing with. So in our case, we're going to be talking about a new equation where EH is equal to ml, okay. EH is still our heat energy, okay, because it's still heat energy we're dealing with. It's heat energy that's added or removed from these substances. So if you think that when you boil water, okay, if you keep continually adding heat to water that's already boiling, it'll convert all that water into steam. But you can't make the water hotter than 100 degrees. All that energy that you're still putting in is converted into steam, and that's this heat energy that we're working out, the latent heat, okay? M is still mass, okay? And the important point I want to make here is mass is measured in kilograms, not grams. If you get given one in grams, you have to change it to kilograms, okay? And this L is our latent heat of vaporization or fusion, okay? So it's our latent heat. Now, we have two different transfers here. We have the transfer here between solid and liquid, which we call the latent heat of fusion. Okay, whether it's going from solid to liquid or liquid to solid, that side is called the latent heat of fusion. And on the other side, between liquid and gas, we have the latent heat of vaporization. Okay, and those are our two for that. You'll see them both on the data sheet as those terms. Fusion is between solid and liquid, and vaporization is between liquid and gas, right? And that means, depending on what the question is asking you for, you're going to be moving between the two of these, whether you're going to work out the latent heat for energy, work out the energy, sorry, required to boil water, or the energy required to be removed to freeze water, okay? So that's me kind of done it in a nutshell for you. There'll be another video in a wee second, another video below this that you'll be able to look at that will give you a couple of worked examples, one of turning something into a solid and one of turning something into a gas, so we can look at the conversion on both sides, okay? And then I'm going to set you loose on the questions that I've given you in the homework, okay? Those questions I want you to have done sort of by Friday, okay? There's only 10 of them. It's not going to be too much work. And the answers will be released on Wednesday for you to self-mark, okay? Best of luck. If you have any questions, you can get me on Show My Homework or on Teams. I'll be on both all week, completely accessible, okay? So if you have any questions, please, please, please do message me. We want to make the most of this, especially for those of you who are considering taking physics further forward. You need to be good at this. Those that aren't, I have a task that's slightly different for you to finish up the week. But to start with, I would also like you working on this calculation here, okay? Best of luck, guys. Alright guys, here we go, a couple of worked examples. And as promised, if you go onto the OneNote, I have embedded in here a lovely, delightful, completely awesome snapshot from the SQA documentation that gives us the specific latent heat and fusion of materials and specific latent heat of vaporization of materials. Now, as a reminder of what I was talking about, vaporization is when we go from liquid to gas, and fusion is when we're going between solid and liquid. Okay, so what we've got here is we've got our first question, first worked example, and what it says is a 5 kilogram bag of ice is left sitting on the counter to melt. How much energy is absorbed by the ice to turn it into water? Okay, so going by all of the stuff we've done all year, the first thing we're going to do, step one, write down what you know. So we know that the mass is 5 kilograms. Now, the other thing that we know here is we know the latent heat of vaporization, of fusion of water, because it's over in this table over here. So the latent heat of fusion for water, right there at the bottom. Okay, so we're going to put that in here as well. 3.34 times 10 to the power of 5. And that's measured in joules per kilogram. Okay, so we know those two things, and we know the equation we're going to be learning about today is EH equals ML. So this is a nice simple one. Mass is 5, substituting in our numbers. L is 3.314, it's 3.34, I've always got pi on my brain, times 10 to the 5. We put that into our calculator. Which I didn't get out before I started the video, but I have now. So 5 times 3.34 times 10 to the 5 is 1.67 times 10 to the 6. And energy is measured in joules. So put our answer on, we double underline it. Our next question, we're going to be dealing with things changing, water changing to steam. Okay, so again, step one, write down what you know. We know that the mass is 2 kilograms. And we know the value for L. We just have to go and get it. So it's up here. So this time we're looking at vaporization because we are moving from water to steam. And that's the bottom one there. 22.6 times 10 to the 5. So I'm going to bring that over here and we're going to put it in there. 22.6 times 10 to the 5. Our equation gets written down, EH equals ML, and so that's going to come out as 2 times 22.6 times 10 to the power of 5, which will give us 4.52 times 10 to the power of 6, again measured in joules. Okay, so there's a couple of worked examples gone through for you. Remember, these questions are generally going to be 3-mark questions if you see them. So you'll get 1 mark there for writing in your equation, 1 mark for substituting your numbers in, and 1 mark for your final answer with unit. Okay, and again, 1 mark, 1 mark, and 1 mark for the same 3 steps. Okay, so it's really important that you show all your work in. I'll say it again. Show all your working. Okay. Good luck with the questions. Answers will be posted on Wednesday, and you submit them to me by Friday, okay? So, best of luck and enjoy.